Good morning, students. Let us draw the shear force at bending moment diagram for a simply supported beam which is carrying eccentric point load. Here you can see we have a simply supported beam capital AB which is carrying some eccentric point load capital W at a distance of small a from capital A and at a distance of small b from B. Now the span is taken as L. Now the first step for this thing is we have to calculate the support reactions. For this thing what I am going to do here is I will consider a reaction RA at point A, and let us consider one more reaction. This is reaction RB at point B. Now considering equilibrium of the entire section, when you consider equilibrium of the entire section, it has to satisfy three different conditions of equilibrium. The first one is sigma fx equal to 0. Algebraic sum of all the forces acting along horizontal direction should be equal to 0, but we don't have any horizontal forces on the beam. That step is neglected. Sigma fx equal to 0. We don't have any forces. Next, let us go with sigma fy is equal to 0. Algebraic sum of all the forces and their components acting in the vertical direction is equal to 0. Now, reaction RA and reaction RB both are acting in the upward direction and only W is acting in the downward direction. So, let us take a reaction RA plus RB minus W is equal to 0, or RA plus RB is equal to W. Let us take this one as the first equation. Now let us take moment at any point. I'll take moment at point A is equal to 0. Moment at point A is equal to 0. Now with respect to point A, reaction RB is making an anticlockwise rotational effect, should be taken as positive, plus RB, and it is located exactly at distance of L. RB multiplied by L minus W is rotating in the clockwise direction, so it should be taken as positive. It should be taken as negative according to the sign convention. So minus W multiplied by, at what distance it is located? A. So I am equating this thing to 0. So RB, you will get this one as W into A divided by L. Now substituting RB in the above equation number 1, you will get RA is equal to W minus RB, that is equal to W minus WA divided by L. So I can write RA is equal to W into L minus A divided by L. Now L minus A, this is L minus A, so we will get B. L minus A is B, so this can be written as WB by L. So we have reaction RA is equal to WB by L. So we got both the reactions. RB is WA by L, RA is WB by L. So I am just indicating them here, WB by L, and this one is WA by L. Reaction RA and RB obtained. Okay, this is it. Now the next thing is we need to calculate the shear force and the bending moments. So for that thing what I am doing here is I'll take a section in between B and C. So let us consider the point where the point load is acting is C. I am just considering a section in between B and C. Let us call this section as 1 and 1. Now this section is located exactly at distance of small x. It is located at distance of small x. Now I am considering right side of the section, towards right side of the section, that means towards point B, Now how many forces are acting towards point B? There is only one force which is acting in the upward direction. I'll draw it here, right, just to see. We have section here, this is section 1 and 1, and towards right side of the section we have only one force, that is WA by L, which is acting in the upward direction. Right side upwards should be taken as negative according to the sign convention, so this should be negative shear force. So shear force at any section X or shear force at any section 1 and 1, right, it is equal to minus WA divided by L. So we don't have any other force in between B and C, so shear force at point B equal to minus WA by L, and shear force at point C is also equal to WA by L, minus WA by L. That means it will be uniformly varying in between B and C, and it will be negative. Now let us consider one more section in between A and C. So before that thing, let us calculate the bending moment. Bending moment at any section 1 and 1 will be equal to, so towards right side of the section, see we have only one force here, so it is creating some anti-clockwise rotational effect. I mean to say it is creating some moment which is bending the beam in the upward direction. That means it is creating some positive bending moment, sagging moment, so it should be taking as positive. So bending moment will be equal to plus WA by L multiplied by X. So this is the bending moment equation we get. Now bending moment at x is equal to 0. That means bending moment at point B will be equal to 0. Why? Because when we substitute x is equal to 0, you will get bending moment equal to 0. Similarly, bending moment at any point x is equal to B. That means bending moment at point C will be equal to W multiplied by A multiplied by B divided by L. So we got bending moment at point C, which is equal to WAB by L. Now we got bending moment at point B, which is equal to 0. So I told you a trick that bending moment for a simply supported beam near the supports will always be equal to 0, and shear force will be equal to the support reactions itself. Okay, now we got two bending moments here. Similarly, I'll take a section in between A and C. Let us take a section in between A and C. Now this section again, let us call this one as section 2 and 2. This section is again located exactly at distance of x from small b, from B. Same thing again towards right side of the section 2 and 2. Towards right side of the section we have two forces. This is W and this one is WA by L, right? Okay. Now algebraic sum of all the forces acting towards right side of the section, right? Already at point C we have calculated shear force at C is minus WA divided by L. WA divided by L, that is negative actually. Now exactly at point C, for the section in between A and C, we are calculating in between section A and C. Now shear force at any section X or shear force in between section 2 and 2, it is equal to algebraic sum of all the forces. See, right side downward should be taken as positive, right side upward should be taken as negative. So this is plus W minus WA divided by L. So you can write this thing as WL minus WA by L, or W multiplied by L minus A divided by L, or WB by L. L minus A can be taken as B. L minus A is nothing but B. So WB by L. So we got positive WB by L. So shear force in between section 2 and 2 will be equal to WB by L. So from point C till point A, it will be WB divided by L. So it will be WB divided by L. So shear force at point C will be equal to plus WB by L, and it will be same as shear force at point A. The next thing is bending moment. This is WA by L, and here we have WB by L. We have a force capital W. This is A and this one is B. Here we took a section that is 2 and 2. It is located at distance of x. Now bending moment at any section 2 and 2 will be equal to, towards right side of the section, WA by L is trying to bend the beam in the upward direction. So it should be taken as positive, plus WA by L multiplied by x. Force multiplied by perpendicular distance. Now this W is pushing the beam in the downward direction, it should be negative. That means it is creating a hogging moment, minus W multiplied by, what will be the distance from here to here? It will be x minus B. This distance is x minus B. X minus B. So we got one equation. The power of equation is 1, variation will be linear. So we need to calculate bending moment at any section x is equal to B. That means at point C we are calculating. Already at point B we have calculated. At point C we will calculate x is equal to B. That means bending moment at point C will be equal to W A B by L. In place of x I am substituting B, minus W multiplied by x, B minus B. So this part here it is equal to 0. So we get WAB divided by L with a positive sign. So already in the previous case we have calculated, right, the bending moment at point C will be equal to WAB divided by L. Now we got the same thing here. Now see, for the same section, if I consider the distance from point A as x, right? Now shear force here, shear force at any section x and x, or shear force in between the section 2 and 2. I'm considering towards right side of section. See, there is no need to consider the section and calculate the shear force, because obviously you know that for any simply supported beam near the support, the shear force will be equal to the support reaction, bending moment will be equal to 0. I can directly take shear force at point A is equal to WB by L. So left side upward is taken as positive, I can take this one as positive. Now bending moment at point A is equal to 0. I can directly take this thing, but I'll explain you how I have approached to this thing. See, I'm considering left side of the section. Towards left side of the section, one force is acting in the upward direction. Shear force at any section X will be equal to WB by L. WB by L. Now left side upward should be taken as positive. This is positive value. Now shear force at point A will be equal to WB by L, as there are no other forces, and again shear force at point C will also be equal to WB by L. So shear force at point C we have already calculated in the previous case. Shear force at point C, WA by L, right? And shear force at point C is WB by L, right? In between the section A and C. There are two values here, minus WA by L, WB by L. Okay, obviously bending moment will be equal to 0. How? Bending moment at any section 2 and 2 will be equal to, so it is creating some sagging moment, so it will be plus WB by L multiplied by X. So shear force is bending moment at any section X is equal to, let us take X is equal to 0, that will be equal to 0 now. Bending moment at section X is equal to A will be equal to WB by L multiplied by A, that is WAB by L. So already we have obtained the values, WAB by L. Now for this same thing we will just plot the shear force and bending moment diagram. So here we have the beam, the simply supported beam. So this is reaction RA and reaction RB. This is WB by L. This one is WA by L. Point A, point B. Here we have point C. This is W. Now just I am drawing some development lines here. Now let us go with the first one, that is shear force diagram. I am drawing SFD here at point A, at point B. Already we know the shear forces. At point B, the shear force is WA divided by L with a negative sign. I am not indicating negative as I am drawing it in the downward direction. Now up to point C, in between B and C, up to point C, it will be WA by L. So just here also it will be equal to WA by L. It will be negative, minus. Next, at point A, we got this one as WB by L. And at point C again we got the same thing, that is WB by L. This one is positive. So this is the shear force diagram. The next one is bending moment diagram. To draw the bending moment diagram, first thing what you need to do here is just draw the baseline. Now above the baseline, exactly at point B, bending moment is 0. Exactly at point A, bending moment is again equal to 0. We got it. Now at point C, we got the bending moment which is equal to WAB divided by L. So here is the point. Now from point A to point C, the variation will be linear. Simply draw a straight line. Now again from point C to point B, it is linear again. So both will be positive only. This is positive, this one is positive. So this one is the bending moment diagram, BMD. That's it. Thank you.